For question 30 from the homework, we're asked the value of the rate constant K for the following reaction. For hypochlorite reacting with iodine to form chloride and hypoiodate. In the previous two questions, you found part of the rate law. And so in the previous two questions so far, you found the rate law with respect to this species and this species in the reaction, right? You found the rate law with respect to hypochlorite and iodide in the reaction. And so far, our rate law looks like rate equals our rate constant times the concentration of hypochlorite times the concentration of iodide to the first and the first. But if we look at this information, and this is where a few of you are getting stuck, is that they also list hydroxide, but we don't see hydroxide over here in the reaction. But if we look at these experiments, especially experiment 3 and 4, experiment 3 and 4 is important because the concentration of hypochlorite stays constant, the concentration of iodide stays constant, and when we double the concentration of hydroxide, we notice that the rate of the reaction changes. The rate actually decreases, it gets cut in half. So that tells us this has an impact on the rate of the reaction, and it has a negative impact on the rate of the reaction because as this concentration increases, our rate of the reaction decreases. But because this has an impact on the rate of the reaction, it needs to show up in the rate law for the reaction. So it needs to be up here in how we calculate the rate of the reaction. And so to find the impact that it has on the rate of the reaction, the equation that I like to use would be concentration 1 over concentration 2 raised to the power of n equals the rate that corresponds to that concentration divided by the rate that corresponds to that second concentration. And again, we're going to be using experiment 3 and 4 because in experiment 3 and 4, we only want one variable. So both other concentrations remain the same. So we've got 0.2 molar divided by 0.1 molar raised to the power of n, where n is our reaction order with respect to that species. So n is what we're looking for. We need that for our rate law. And that's going to equal, let's see, 0.028 divided by 0.056. So we divide, and I get 2 to the n equals 0.5. We're looking for n, so to get rid of, right, to get n, what we can do, so again, we're looking for that exponent, right? We can take the log of both sides. So if I take the log, that'll get us for n, that'll solve for n. And I take the log here of that. And so the log of 2, I get 3.01. And I get a negative 3.01. So I want to find out what n is. I divide both sides by 3.01, and n is negative 1. So the impact, right, that hydroxide has on the reaction, we're first order with hypochlorite, we're first order with iodide, and with hydroxide, we've got an impact of negative 1. Now that we have the full rate law, we can find the rate constant for the reaction. So we had to do all that work to find the full rate law. Now that we've got the full rate law, to find the rate constant, all we want to do is just pick one experiment, because any one of these experiments would work, because I know these 3 concentrations and I know the rate of the reaction when I have those 3 concentrations. So that lets me plug in rate, all 3 concentrations, and now I can solve for K, my rate constant. So to answer this question, right, there's part A, this is part B, right? So using experiment 1, we'll just say, okay, the rate is 0.038 molar per second. I don't know my rate constant, but I have that rate when I've got 0.025 molar to the first, 0.0025 molar to the first, and 0.1 molar to the -1. Raise those, multiply them, and when I do that, I get, let's see, 0.038 molar per second times K times 6.25 times 10 to the -4. And when we look at units, that would be molar. So I divide that across, so I've got 0.038 molar per second equals my rate constant times 6.25 times 10 to the -4 molar. Divide both sides by that concentration, 6.25 times 10 to the -4. 6.25 times 10 to the -4. Divide that across, and I get a rate constant of approximately 61. And this is this ends up being first order overall, so 61 inverse seconds. It's first order because when we multiply, we would add our exponents together. So 1 plus 1 is 2, plus -1 brings us back down to 1. So overall, be a first order. It would look like a first order, so we would have the units of a rate constant need to be inverse seconds for a first order reaction. So yes, to find the rate constant first, we had to find the full rate law for the reaction, and that included using hydroxide, because looking at these two experiments right here, we see that changing the hydroxide concentration changes the rate of the reaction.